Bismillah wa salatu wa salamu ala rasulillah. Welcome to General Chemistry with Dr. Zainab. Today we are going to solve recitation problems for chapter 5, which is about thermochemistry. So let's start by problem number 1. A sample of gas at 15 atmosphere and 10 liter is allowed to expand against a constant pressure, external pressure, of 2 atmosphere at constant temperature. Calculate the work in the unit of kilojoule for the gas expansion. And here I give you that 1 atmosphere equal 1.013 10 to the power 5 Pascal. And there will be also another relationship that you will use, PV equal nRT, which is the ideal gas law that we will see in chapter 10. Yes. Okay, so you need to use this relationship too. So let's make a scheme. So we have a sample of gas here that is at P1 equal 15.0 atmosphere and a volume V1 equal 10.0 liter. And it is allowed to expand, meaning the volume will increase. Okay, so it was here, now it's V2. We have P2 external pressure equal 2.00 atmosphere, and we'll have V2. Then we know it's expansion. This one will be bigger than V1. Okay, and what is asked is the work in unit of kilojoule for the expansion. So we know that W in this case equal minus P delta T. So here, which pressure should we consider? We should consider the external pressure, which is 2 atmosphere. So that means minus P2 delta V. And delta V is equal to minus 2 V2, V final, minus V1, V initial. So how can we get V2? So we know P2, we know V1, but we don't know V2. So let's use the ideal low gas. So we know that P1, V1 equal nRT. The temperature is constant, and we say have the same number of mole for the gas. We know that P2, V2 equal also nRT. So if I have the ratio between these two, meaning P2, V2 divided by P1, V1 will be equal to 1. So I can deduce the value of V2 will be equal to P1, V1 divided by P2. Okay, so this is how I get the expression for the final volume. So I can put it in my expression here. W will be equal to minus P2. So V2 is P1, V1 divided by P2 minus V1. So the P2 will remove here. So we have minus P1 V1 plus P2 V1. Okay, so I can have W equal V1 or minus V1, yes, times P2 minus P1. Okay. So this is the expression of the work that is done. So W will be equal V1. I know it's 10 liter, so be careful here. It needs to be put in meter cube, right? So I have 10.0, 10 to the power minus 3 times P2 minus P1. I know that delta P here, P2 is 2 atmosphere, 2.00 minus 15.0, but it's in atmosphere, so I need to multiply everything by 1.013 10 to the power 5 to have it in Pascal. And if you calculate W minus 13.2 kilojoule. Okay. So we use the fact that it's an expansion, so we know that W will be equal to minus PD delta V, and it will be positive if it's a work that is done on the system, and negative if it's a work that is done by the system to the surrounding. Okay, so here we have P that is increasing. So here, if you have a piston, you know that the piston is moving up. So this is the work done by the system to the surrounding. So that's why it has a negative value, you have minus 13. So this is logical, okay? Here you need to use the ideal gas law just to have the expression of V2, and you can see that it is like a V delta P, okay? Okay, so this was it for this first exercise. So just use minus P delta V as we discussed in the class, and this additional relationship between which is the ideal gas law that we will see in chapter 10. Okay, let's move to exercise number 2. As a system increases in volume, it absorbs 52.5 joule. Absorb meaning it's taken by the system, so this is positive, okay, of energy in the form of heat. So we have Q that is positive from the surrounding. The piston is working against a pressure of 380.0 millimeter of mercury. So working against the pressure, so we know that W will be negative. The final volume of the system is 58.0 liter. What was the initial volume of the system if the internal energy of the system has decreased by 100 or 2.5? Decrease meaning delta U negative here. So we have delta U equal to minus 102.5 joule. Here we have millimeter mercury, and I give you the formula to go from millimeter mercury to Pascal. Okay, so we know that we have similar system than in exercise 1, problem 1. So we have a system with V1, okay, and it increases in volume. We go to V2, and we have the external pressure P that is given, okay, 380.0 millimeter of mercury, okay, and we know that final volume is 50. The final volume of the system is 58.0 liter. So now what is asked is V1. We don't know what is V1. Okay, so we know that it is absorbing energy in the form of heat. Q is positive, meaning Q equal plus 52.5. It is doing work against the pressure. We know that W should be negative, and it's a P delta V work, so W will be equal to minus P delta V, meaning minus P V2 minus V1, okay? And we know that the total internal energy change will be equal to Q plus W, and the value is minus 102.5. So I know that Q minus P V2 minus V1 equal to delta U. Okay, so now I will use this expression to give V1, which is the one I'm looking for. So I know here that P V2 minus V1, if I put it in the other side, will be equal to Q minus delta U, meaning V2 minus V1 equal Q minus delta U over P, okay? So I can have the expression of V1, which will equal to V2 minus Q minus delta U over the pressure. So this is the expression of V1. Let's get the numerical value here. So we have V1 be equal to V2. It's in liter, so I need to have it in meter cube, minus, so Q is 52.5, minus delta U. Delta U is minus 100 joule. So it's going to be plus 102.5 and divided by the pressure. So the pressure here is in millimeter mercury. So I know that 750.1 is corresponding to 10 over 5 Pascal, 10 to the power 5. So if I have 380.0, I multiply by 10 to the power 5 and I divide by 750.1. Okay, so here the pressure is 380.0, 10 to the power 5 divided by 750.1. Okay, so this is the expression for the pressure. And V2, if you calculate the numerical value, V2 will be equal to 0. This is V1, sorry. We are looking for V initial. 0.0549 meter cube, or 54.9 liter. Okay, and we have V1 smaller than V2 as expected. Okay, so here just check the signs for Q and W. Use the expression of delta U in function of Q plus W, and we have the numerical value already of delta U. You compute it and you get the expression of V1, and here you can calculate it. Okay, so we have been working we have been using W equal to minus P delta V 2 times now. Okay, so P delta V work is something that you should know. Okay, and when it's energy that is absorbed by the system, it's positive. If it's released, then it's negative. Okay, and let's move to problem number 3. What is the change in internal energy for a process where a piston expands against 1 atmosphere of pressure from 11.2 liter to 29.1 liter? In the process, we know that 1037 joule of heat is absorbed. Okay, absorption, so we know it's positive. Q will be positive. We know that it's a piston expansion, again, P delta V work minus P delta V. And here, what happened? We have an increase of the volume. So 11.2 to 29.1. So we know that it's the same, similar to what we get before. So we have V1 and V2 that increases. So we have work done by the system to the surrounding. So W minus P delta V, we know that it should be negative. Okay. So here, what is asked? What is the change in internal energy? So delta U, we know that will be equal to Q plus W. Q is positive. This is what we get. So Q, and we know that W is minus P, 1 atmosphere delta V. Okay. So let's compute. You know that delta U will be equal to Q, that is positive, 1037 minus P. Here is 1 atmosphere, and we know that 1 atmosphere we need to multiply. So from here, 1 atmosphere equal 1.013 10 to the power 5. So 1.013 10 to the power 5. So don't forget to convert. And we multiply by delta V. So we have 29.1 minus 11.2. But this is in liter, so we need to convert it to meters cube. So 10 to the power minus 3. Okay, and delta U, if you compute it, it will be equal to minus 776 joule. Okay, so here be sure that you know that absorption means that it is done to the system. So Q is positive. Piston expansion work, we know that is P delta V, and here increase in volume delta V positive minus P delta V, the work is negative. Okay, and don't forget to convert liter into meter square if you have everything in the Pascal. If you have the pressure in Pascal, so everything should be in meter cube for the volume. Okay, so again we have W by P delta V. So this one you should know it by now. Okay, let's go to problem number 4. The overall reaction in a commercial heat pack can be represented as iron solid react with oxygen gas to give iron oxide solid. And we have delta H equal to minus 1,652 kilojoule. So we can check first that the reaction is balanced. So 4 iron, 6 oxygen, 6 oxygen. Okay. How much heat is released when 4 mole of iron is reacted with excess O2? So directly when you see this, you know that it's delta H per 4 mole of iron, but it's also delta H per 3 moles of oxygen gas that give delta H per 2 mole of iron oxide. Okay, so if I have 4 mole of iron, if I multiply this by 4, I know that the value of the energy which is released, so here I don't need to express the sign. I know it's already released, should be negative. So the energy, the heat that is released, Q released, will be equal to what? Delta H. But here, check it out. We have 4.00 mole of iron. That means how many significant figures I have? I have 3 significant figures. So my energy should have also 3 significant figures. So it's 1.65 10 to the power 3. Okay, so if you write it, it is 1650 kilojoule. Okay, if you give me 1652, I understand, but the correct result is 1650 because of the number of significant figures for the number of moles. I hope this is clear. Okay, so the value numerically is the same, it's just that I have it with 3 significant figures, so I'm not sure about this one, whether it's 2 or 0, I don't know, but if it's 3 significant figures, it's 1.65 10 to the power 3, so 1650. Okay, so this is something that can happen. You have 4 significant figures, but you have 3 here, so the result should have 3 significant figures. So 1.65 10 to the power 3 kilojoule. Okay, and it's released, so we know already that it's negative. And don't forget that this is when it is balanced in the stoichiometric amount, you know that delta H is per 4 mole of iron, 3 mole of oxygen, and 2 mole of iron oxide. For question B, how much heat is released, again, when 1 mole of iron oxide is produced? So I know that this is for 2 mole. If I have 1 mole, that means I have half less energy, right? And still, again, it is 3 significant figures. So I know that Q released normally should be equal to the number of mole of iron 2 oxide times delta H divided by 3, here 2 moles of iron 2O3. This is solid. Okay, so here is 1 mole, so 1.00 times, this is the value, the absolute value. Okay, so we don't take care about the sign because we know that it's released, 1652 divided by 2. Okay, 2 moles. So here, if you calculate it, yes, so we keep 3 significant figures, 826 kilojoule. Okay, I hope this is clear. This ratio is coming directly from the balance reaction, and then you just multiply by the current number of mole to get the energy. Okay, let's move to the last question for this exercise. There is C and D. So how much heat is released when 1 gram of iron is reacted with excess oxygen? So I know that iron is my limited reactant. So how I'm going to do that? Here again, I know that delta H is for 4 mole of iron S. Here, what is the number of mole I have? I have an iron solid that will be equal to the mass of iron solid divided by the molar mass of iron solid. So here you can get it from the periodic table. So I know that Q release will be equal to the number of mole of iron solid times delta H, absolute value, divided by 4 mole of iron solid. Okay, so we can get the numerical value. Q release will be equal to N iron, so I have 1.00 divided by 5.85, the molar mass of iron that you can get from the periodic table, multiplied by 1652 divided by 4. Okay, so the Q, if you calculate it, will be equal to So 3 significant figures for 4. So 3 significant figures for the result. 7.39 kilojoule. Okay. Here I could directly calculate from the number of mole of iron because I know that it is the limiting reactant, because here it's expressed that oxygen is in excess. But let's check the case for D. So how much is released when 10 grams this time of iron is reacted with 2 grams of oxygen? So when I have the masses for 2 of the reactant, I know that what I should first check is which one is in excess. From my stoichiometry, I know that I should compare number of mole of iron solid divided by 4 and number of mole of oxygen gas divided by 3 to know which one is in excess. So the number of mole of iron solid divided by 4 is the mass of iron, 10.0, divided by the molar mass, 55.85 times 4. I need to calculate it. And the number of mole of oxygen divided here. Okay, let me write it here. The number of mole of oxygen gas divided by 3 will be equal to the mass of oxygen, 2.00, divided by the molar mass of dioxygen, so 32, multiplied by 3. So the value here is 0.0200 mole, while here it is equal to 0.0448 mole. So which one is in excess? Iron is in excess. So I know that number of mole of iron divided by 4. So I will write it here. Number of mole of iron solid divided by 4 is bigger than number of mole of oxygen gas divided by 3. So I compare just 0.0208 and 0.0448. Okay, so oxygen is my limiting reactant. So if I want to calculate the energy, I need to use the number of mole of oxygen. And from the reaction, we know that it's delta H per 3 moles of oxygen gas. So Q will be equal to N oxygen times delta H, absolute value, divided by 3. And we already calculate NO2 divided by 3, which is this value. Okay, so the Q release will be equal to 0.0208 times delta H, which is 165.2. And the numerical value is 34.4. So this is a good revision for chapter 3. So when you have a reaction, chemical equation, you need first to check its balance. And then here, from the thermodynamic perspective, you know that delta H is released for the stoichiometric ratio. So I have delta H by 4 mole of iron, delta H by 3 mole of oxygen, and delta H by 3 mole of iron oxide. Okay, so if I have the masses of iron and oxygen, I first need to calculate their number of mole and know which one is in excess, which one is the limiting reactant. And then from there, I can calculate the energy. So here, in this case, O2 was the limiting reactant. Okay. So that's it for exercise number 4. I hope it was clear. Let's move to exercise number 5. Consider the combustion reaction of propane. So propane reacts with oxygen to give carbon dioxide and water, and we have delta H minus 2221 kilojoule. That means it's exothermic. Okay, assuming that you want to produce an amount of heat of 1.3 10 to the power 8 to inflate a balloon, what mass of propane must be burned to furnish the amount of energy, assuming that the heat transfer process, so we are transferring heat, is 60% efficient. Okay, so how can we solve this problem? So let's do it step by step. So here we know that delta H is for 1 mole of propane. gas, you know that is delta H per 5 mole of oxygen, this mole, and it's giving delta H per 3 moles of CO2 gas and delta H per 4 mole of water. Here what is interesting us is for propane. So we know that here, if I want to know the Q that is released, it will be equal to number of mole of propane times delta H in absolute value divided by 1 mole of C3H8 gas. But this will be the case if I have something that is 100% efficient. Here I know is 60%, so I need to multiply by 0.6. Okay, and this value is also given by 1.3 10 to the power 8 joule. So I have the numerical value and I have the expression. Okay, because here what is asked is what is the mass of propane. From the chemical equation and the value of delta H, I can get the number of mole. And I know that the number of mole is also mass of propane divided by molar mass. And you can calculate the molar mass of propane. 44.09 gram per mole. So I can have the expression for the mass here, okay? So I have mass over molar mass multiplied by delta H multiplied by the efficiency equal 1.3 10 to the power 8. So I know that M, this is also Q, right? So M will be equal to Q times molar mass divided by 0.6 delta H. So this is the expression for the mass of propane. Okay, so the mass will be equal now to Q is 1.3 10 to the power 8 joule times the molar mass. So everything should be in the SI unit. So here I need to convert in kilogram. 10 to the power minus 3. Okay. Delta H 0.6 times 2221 10 to the power 3, but I have everything in joule. And M will be equal to 4.3 kilogram or 4.3 10 to the power 3 gram. Okay, so this is here how you solve this exercise. So you have the value, numerical value, the heat that you produce, you want to produce 1.3 10 to the power 8. So what is asked is what mass of propane should be burned from the chemical equation that is balanced. Okay, so you have 3 carbon, 8 hydrogen, 8 hydrogen, 10 oxygen. So you have 2 times 3, 6 plus 4, 10. Okay, and I know that this is delta H per 1 mole of propane gas. Okay, and the Q is obtained by the number of mole times delta H multiply here by the efficiency. So it was 100%, it will just be 1, but here it's 60%, so I have a corrective factor that is 0.6. Okay, and I know that the number of mole is also mass divided by molar mass. I can get the expression of the mass using the energy that is released, the molar mass, and delta H from my chemical equation. And you can calculate it to get the mass. Okay, let's move to problem number 6. For the following reaction, so hydrogen react with oxygen gas to give water, we have delta H minus 572 kilojoules. So this is exothermic, just by looking at the sign. Okay, how much heat is evolved for the production of 1 mole of water? So what do we do? First, check if it's balanced. So we have 4 hydrogen, 2 oxygen, 2 oxygen, balance. What does it mean? That if I have the reaction, I have delta H equal minus 572. I know that this is delta H per what? 2 moles of hydrogen gas, but it's also delta H per what? 1 mole of oxygen. Very good. And I know also it's delta H per 2 moles of water, liquid. So if I have 1 mole of water that is produced, this is for 2 moles. So if I have 1 mole of water, I know that Q will be equal to the number of mole of water times delta H divided by 2 mole of water liquid. Okay, so this is equal 1. So this is 1 times 572 divided by 2. Okay, and 572 divided by 2 will give you 286 kilojoules. Okay, so for 2 mole I have 572, and for 1 mole I have half of it. Okay, this is logical. How much heat is evolved when 4.03 grams of hydrogen is reacted with excess of oxygen? So I need to know for 4.03 grams of hydrogen, what will be the number of mole? Okay, so here is, you can calculate the number of mole of hydrogen. So it's the same. We have Q equal number of mole of hydrogen gas multiply by delta H for 2 moles of hydrogen gas. Okay, the number of mole of hydrogen gas is 4.03 divided by 2 times 1.008 multiplied by delta H here, which is 572, and divided by 2. Okay, and here when you check that 2.1008 actually is equal here. So you can calculate it for 0.03 divided by 2 times 1.08 is actually equal to 2. Okay, so I'm calculating when I have 4.03 grams of hydrogen is actually 2 moles of hydrogen. And I know that this is for 2 moles of hydrogen. So when you calculate it, you will get actually 572. Because simply for 4.03 grams, if you calculate, this is equal to 2 moles. Okay, and the 2 will cancel and you get 572. Okay, so this is logical. We know that this is the heat that is released when we are having 2 moles of hydrogen. So if I use 4.03 grams, if I calculate the number of moles, it's actually 2 moles. So when I calculate it numerically, I should have delta H in the absolute value. Okay, so, and there is a last question for this problem. C. Here where I have the masses for both of them. So the total volume of hydrogen gas needed to fill the Hindenburg was, okay, so problem 6 is finished. No, there is total, question number C. Okay, the total volume of hydrogen gas needed to fill the Hindenburg was 2.0 10 to the power 8 liter at 1 atmosphere and 25 degrees. How much heat was evolved in the Hindenburg disaster, assuming all the hydrogen gas was burned? So this was something that happened in 1937. Okay, you can see on the picture. So they were doing air flight, and this disaster happened. There were some casualties, and we will see that the amount of energy that was released was huge. Okay, it was really huge, and that's why it was so catastrophic. But let's go to the chemistry side. So the total volume of hydrogen that was needed is V, and we have the pressure and we have the temperature. So what is the relationship we can use? Yes, the ideal gas law, PV equal nRT. So here we have the pressure, we have the volume, and we have the temperature. The nR is known. So we can calculate the number of mole of hydrogen. Exactly. Because here we still know that this is delta H per 2 moles of hydrogen gas. So if I want to know the heat, Q, I know that I should have the number of mole of hydrogen gas times delta H divided by 2 mole of hydrogen gas. Okay, so here we need to calculate N by using the ideal gas law. So we have N equal PV divided by RT. Okay, and everything should be given in the SI unit. So R is equal to 8.31 SI. T will be equal to 273.15 plus 25. So it's going to be in Kelvin exactly. So 298.15 Kelvin. Okay, we have the pressure in atmosphere. So we know it's 1 atmosphere, 1.0 or 1.013 Pascal. So we have everything we need. So we can calculate the Q that is released. And here, don't forget to convert the volume here in meter cube. Okay, so we have Q here. N is PV divided by RT times delta H divided by 2 mole of hydrogen gas. So this is the expression for the Q that is released. Let's get the numerical value. So Q equal P, we know that is 1.013. Is it 10 to the power 5? For the pressure? Yeah, I forgot the 10 to the power 5. 1.013, 10 to the power 5 Pascal. Okay, 1.13, 10 to the power 5 times the volume. So 2.0, 10 to the power 5, because I multiply by 10 to the power minus 3 to get it in meter cube. Okay, times delta H 572, also 10 to the power 3, because I wanted to have it in joule. Okay, and R 8.31, the temperature 298.15 RT, and multiply by 2. And Q, if you calculate it, is equal to 2.3. Check the power here, 10 to the power 9 kilojoule. Okay, so this is a huge amount of energy. So you can imagine how disastrous this accident was. So 10 to the power 9 is like billion. Okay, so this is a huge amount of energy that was released during this accident. Okay, so this was for exercise number 6. So same, you have the equation, you check that it's balanced, you know that you have delta H, so it's delta H per stoichiometry for the reactant and the products. So if I want to have Q release for any number of mole, I just multiply the number of mole by the relationship I get from the balance reaction, and then I can calculate it. Here we have been using PV equal nRT. So if it is a midterm or exam, since we didn't do chapter 10, I will give you this relationship. Okay, but now you should know it that PV equal nRT is the ideal gas law. And if you have pressure, volume, and temperature, you can deduce the number of mole from this expression. Okay, let's move to problem number 7. Consider the dissolution of calcium chloride. So we have calcium chloride solid that give calcium 2 plus aqueous and chlorine aqueous. So we have delta H equal minus 81.5 is again exothermic. So in a specific experiment, 11 grams of calcium chloride was dissolved in 125 grams of water at 25 degrees. Calculate the final temperature of the solution, assuming no heat loss to the surrounding. So the specific heat of solution is 4.18 joule per degree per gram. So first, what do we know? Here we have water. So I have water. Water with a mass M equal 125 grams. And what do? I add here calcium chloride. Okay, with a mass M. And put water here just to distinguish them. M equal 11.0 gram. Okay, and was dissolved in water 125 grams of water at 25 degrees. And I know that the temperature of the water was 25.0 degrees. Calculate the final temperature of the solution, assuming no heat loss to the surroundings. So there is no heat loss. So this is isolated, no heat loss. Okay, so I know that the amount of heat that is lost, Q, will be negative. Okay, so it's lost, and the expression, you know that Q water should be equal to minus Q reaction. Okay, because it's isolated, so I've taken from Q water plus Q reaction should be equal to 0, because this is closed. There is no heat that is lost to the surroundings. So I have Q water plus Q reaction equal 0. So that's why Q water equal minus Q reaction, or Q reaction equal, because I'm looking for the Q of the reaction, is minus Q of water. So now, what is the specific heat for water? So I know that Q water, I have the specific heat, so it's Sm delta T. Okay, meaning Sm T final minus T of water, which is the T initial. Okay, so I know that Q reaction is equal to minus Q of the water. So I have minus Sm T final minus T of the water. Okay, so this is one expression. Well, how can I calculate it else? So this is Q water, Q reaction equal minus Q water. Here I have the mass of calcium also, and I have that it is delta H minus 81.5. So what can I say about it? If I have a mass of 11.0 gram of calcium chloride, can I know the Q reaction? The answer is yes. From the previous exercise, you know that the Q reaction will be equal to N calcium chloride multiplied by here delta H, and here is 1. Okay, so 1 mole of calcium chloride. Okay, and the number of mole of calcium chloride will be equal to the mass of calcium chloride divided by the molar mass of calcium chloride. And the molar mass of calcium chloride, you get it from the periodic table, 110.98 grams per mole. So I can get my expression for T final. So I have Sm T final minus Tw water equal here N calcium, meaning M calcium, chloride, divided by molar mass, right, times delta H. Here I'm talking about the heat that is released, so I know that it's also going to be negative delta H. I need to use minus 81.5 delta H divided by 1, so delta H. So T final, the expression will be equal to T initial, so T water, and here the minus Sm minus MCa2 delta H divided by Sm, or M water, multiplied by molar mass of calcium. Okay. So let's go up here to calculate it. I have T final. Tw at initially is 25 degree. 25 plus 25.0. Okay. Here I have minus delta H, so plus 81.5 10 to the power 3 multiplied by M calcium 11.0. I have also a mass down, so I can keep gram because the 10 to the power minus 3 will be cancelled. Okay. Multiplied by 11 and divided by the molar mass of calcium chloride, 110.98, multiplied by the specific heat, 4.18, multiplied by the mass of water, 125. Okay, so T final is equal to 40.5 degree. Okay, so here we have to use two different expressions of Q reaction using the fact that we have water with a specific heat at 4.80 and the mass, so Sm delta T, and we know that Q reaction is equal to minus Q water, so minus Sm Tf minus Tw. And we also know that delta H is for 1 mole of calcium chloride. So if I have this mass, it's corresponding to this number of moles, so M divided by molar mass, and here you have to multiply by delta H. So the number of mole multiplied by delta H, and it's per 1 mole of calcium chloride. And from there, these two expressions, they are equal. So minus Sm delta T, T final minus T water, equal the mass divided by the molar mass multiplied by delta H. And from there, I can remove Tf to the expression. So Tw minus M calcium chloride times delta H divided by Sm multiplied by the molar mass of calcium chloride. And if you cut it out minus here, we need to consider the sign because I am considering the reaction. Okay, so minus Q water minus Sm delta T, and here the heat that is released is the number of mole of calcium multiplied by delta H. Okay, so you can get the numerical value of T final. All right, let's move to exercise number 8. When a sample of metal weighing 150 grams at 75 degrees is added to 150 grams of water at 15 degrees, the temperature of the water raises to 18.3 degrees. Assuming all the heat lost by metal is absorbed by the water, what is the specific heat capacity of the metal? So let's try to represent what is happening here. So I have a piece of metal here, and the piece of metal is M equal 150.0 grams. Okay, and I will call it M1, and I have T1, which is the temperature of the metal at 75.0 degrees. Okay, and I put it in water. So I have my metal now inside water, and the water is water is added, and you have M2, which is the mass of water, equal also 150.0 grams. And it was initially at a temperature T2 equal 15.0 degrees C. And everything goes to a final temperature Tf equal to 18.3 degrees. Okay, so if the final temperature of the water is 18.3 and you assume there is no heat that is lost, meaning also that this final temperature is both for water and for the metal. So it's final temperature for all of the system. So if you consider our system as the metal system, that means water will be the surrounding. Okay, so water is my surrounding, and I know that Q reaction plus Q surrounding should be equal to 0. So I know that Q reaction is equal to minus Q of the surrounding, which is minus Q water. Okay, and can I calculate the Q of water? If I know the mass, I know that the specific mass also from the previous exercise, but also from class, is equal to 4.18 joule per degree per gram. Is minus Sm delta T, T final, minus which temperature? Initial for water, so minus T2. So this is the expression that I get when I use the fact that Q reaction is equal to minus Q surrounding, which is minus Q water, so minus Sm delta T. Okay, here what is asked is the heat capacity of the metal. I also know that the Q reaction is equal to what? C delta T. Okay, but here delta T1. So C of T final still final because it's the final for water, but also for the metal. But what was the initial temperature for the metal? T1. Okay, and I have Q reaction, two expressions that are equal. So I have minus Sm T final minus T2 is equal to C times T final minus T1. Okay, so I can get C here. C equal minus Sm T final minus T2 divided by T final minus T1. Okay, so this is the expression for the heat capacity of the metal. So C will be equal to minus 4.18 multiplied by the mass of water, 150.0. T final 18.3 minus T2 15.0 divided by T final 18.3 minus T1, which is the initial temperature of the metal, 75.0. And C, so I have three significant figures for here, 0.33. The result should have three significant figures. The 0.244 joule per degree. Okay, so this is how you get it. So first, you have to get the fact that you're having a metal inside water, isolated. So water is the immediate surrounding, and the pellet or the metal, sample metal, is my system. And I know that it's an isolated system, so Q reaction plus Q surrounding should be equal to 0. So I can get the Q reaction using the specific heat of water minus Sm delta C. But I also know that it's the heat capacity of the metal times delta T. So I can get the heat capacity of the metal like this. So this is a typical exercise that you can get, particularly CH8 and also 7. Okay, so these are using the same principle. Here, what is asked is C, the heat capacity of the metal, while here what was asked was the final temperature. So please make sure that you are able to do with very easily all of this type of exercise for chapter 5. So that's it for this recitation. See you again next time.